Hey guys, welcome to my instrumentation class. So I'm Sibshanko Mukherjee. So I'm going to say something about instrumentation at first, and after that we're going to go deep in the different chapters and different topics. So at first, let us discuss about what is instrumentation, and another thing is with that instrumentation, that is the instrumentation and control engineering. So let's start. What is instrumentation? We can say that the instrumentation and control engineering is really a very much good branch of engineering which studies the measurement and the control processes of the variables, the design and the implementation of the systems that incorporate them. So from there we can really include many of the things, that is the pH value, force, speed, the humidity, the temperature, pressure, and blah blah blah, many of things of the there. So really this branch is a very dominating branch which is going to be in the future. So the IC, that is the instrumentation and control engineering system, that is the two branches are over here on the same way, but these two are totally little bit different, not totally, but I'm want to describe it that how they are different. So instrumentation is a science of measurement and control of the process variables within a production or manufacturing area. But in case of the control engineering, also the control systems engineering is the engineering discipline that applies the control theory to design a system and that desire with the desired behaviors. So we came to know that what is a instrumentation engineer. So really we all know that many different things which are coming on our way, that is in today's markets, and all those things really they are included. The instrumentation engineers are totally included in them, because many instruments that which you are using nowadays, that is the phones, laptops, your cars, your remote cars, whatever you are going to say, that even the malls, the doors, the many instrumentation instruments are there which are included in our life, in our daily life, which is having many ideas, totally different ideas which are included over there. So totally they're coming from the instrumentation and the control engineers. So they are the main, I'm going to say that they're going to be the future, because they are the one who is making our system totally different from our mind. Because whenever you're getting a new type of instrument where you are always in a hurry to know that what is inside it and how it is working, and what and why is this type of things are coming. So these are the things which are coming. So for this we are going to give a clap for the instrument and the control instrumentation and the control engineers, because they are making our world a different one, because they are always included in many of the branches. They are helping many different fields, because even an electrical engineer also need an instrumentation and control engineering nowadays. I'm not saying it before, because many manual systems, I'm not saying about that, but I'm saying about the systems which are going in a flow in nowadays. So at first we are going to say that as a profession, high demand for the engineering professionals is found in the fields associated with process automation. So nowadays we came to know that specializations include the industrial instrumentation, the system dynamics, process control, and control systems. So like this one, there are many steps are there. So we are included over here. So instrumentation engineers are totally different from other engineers, I'm saying you. And now the goals of the work of an instrumentation engineer and a control engineer are like this way, that is the productivity, optimization, stability, reliability, safety, continuity. These are totally, there should be in the mind of an instrumentation engineer. So it should not be not in the mind of instrumentation engineer. I'm saying you that these are the points should be there, because they are the one who is changing the world. Yeah, so you have to take the market up with your instruments. So you have to do this type of things. So now if we are going to discuss many of the systems which are which we should at first know that how many instruments are there, many small devices are there which are used in the which are used in what I can say nowadays, many systems, many devices which are includes many small chips and all those things which are you are also having in your phone, through which you are saying. So why these are happening, how they're working, are totally dependent on the electronics part. So the how the electronic machines are working with many different ways, that is the instrumentation, and how they are planned and how they are being chipped and how they are being what I can say, the way they are being placed in the motherboard. That is the way how what an instrumentation and the control engineering is doing. So at first we are going to say that many systems, like if I'm taking the RTTs, the thermistors, the temperature sensing thermometers, many other things which we should at first know that how they are being used. So if we are taking a topic, that is thermistor, so let us discuss about the thermistor at first. So if we are going to take a thermistor, so what is thermistor? As we people, what we know, what is a thermistor, what is coming into your mind? So at first I should know that thing, na? So but I can ask you one thing, that is, where and why is this thermometers thermometers are used? So for what we use thermometer? The thermometers are being used for the temperature sensing. So from there we are taking the therm. So therm means we are taking the word from the thermal, and as we all know that in the electricity chapter we all read that resistance. So resistance, by which we are used to measure the resistance, resistor. So the two words, that is, on combining these two words, we are getting the thermistor. So first is the thermistor, and after that first is the thermal, and after that is the resistor. So both are making a thermistor. So what is a thermistor? A thermistor is a type of resistor whose resistance is dependent on temperature. So that means a thermistor is a type of resistor whose electrical resistance varies with changes in temperature. So whenever the temperature change, there is a change in the resistance. What we all people know, that whenever in a conductor, whenever there is a change in temperature, there is a change in the flow of the electrons. That is, whenever we are increasing the temperature, there is a flow of electrons is less, because the random motion of the holes are obstructing the that is the resistance, or increasing the resistance. And whenever it is on a in a room temperature, whenever the conductor, it flows in a steady way. So that is in a linear way, that I'm saying. So let's now take that is a thermistor is of two types. The thermistors is of two types, that is the NTC and PTC. The NTC stands for the negative temperature coefficient, and the PTC stands for the positive temperature coefficient, where the thermistors are widely used in a rush current limiters, temperature sensors, the self-resetting overcurrent protectors, the self-regulating heating elements. Like this way, many in the fields, many fields there are, that is the thermistors are used. So now we are taking that is there are two opposite fundamental types, that is the NTC and the PTCs I'm talking about, where in case of the NTC, the resistance decreases as the temperature rises. So there is a decrease in resistance when the temperature rises. So these are the negative temperature coefficient, that is commonly used in the temperature sensor or in a series with a circuit as an inverse current limiter. So there are many machines, but we are just discussing on this too. So it is a brief description of the NTC, and a little bit be a brief description of the PTC I'm also saying about, that is resistance increases with rise in temperature. It's just the opposite. So the resistance increases with the rise in temperature. It's the normal case in case of the conductors. So that is the PTC thermistors are commonly installed in series with a circuit used to protect against overcurrent conditions as a resettable fuses. So these are the things which we should keep in our mind, that is what the NTC is doing or what the PTC is doing. So what the NTC is doing, NTC is doing, that is where resistance decreases with the rise in temperature, and the PTC where the resistance increases there when there is a rise in temperature. So from this point, from the next point we are just coming, that is there are how the thermistors are made. So how the thermistors are made, that is they are made with doping elements. Yeah, the thermistor is generally produced using the metal oxide, the powdered metal oxides. Yeah, with vastly improved formulas and techniques over the past 20 years. The NTC thermometers was first invented by Michael Faraday in 1833, but the NTC thermometers can now at least achieve accuracies over a wide range of temperatures, as we can say that from the plus minus 0 degree, 0.1 degree or 0 degree if I am taking, to plus minus 0.2 degree. Yeah, and from another from range to or 0.2 degree from 0 to 70 degree with excellent long-term stability. This is for the NTC. The NTC thermometers elements come in many styles, such as the axial leaded glass encapsulated, the glass coated chips, epoxy coated chips, that is with bare and insulated lead wire, the surface mount, as well as like rods and disc. And there are many types, that is a bead type, rod type, disc type. There are many types of thermistors, so we can get in many shapes. Yeah, as there is a typical operating temperature range of a thermistor, that is the minus 55 degrees Celsius to plus 150 degrees Celsius. Though some glass body thermistors have a maximal operating temperature of about plus 300 degree. So as I was saying in the beginning, that's at the starting of the class, that's there are RTDs. So what are the RTDs? So now I'm just going to say that these thermometers are totally different from the resistance temperature detectors. The resistance temperature detector, that is the RTD, stands for resistance temperature detectors. So they are in that case, the material used in thermistor is generally a ceramic or a polymer, while the RTDs use the pure metals. So their temperature response is totally different for these two devices. That is, the thermistor is totally different because it is made up of ceramic or polymer, and where the RTDs are totally made from the pure metal conductors. So there should be a difference. So now we can say that the RTDs are useful over the large temperature ranges, while the thermistors typically achieve a greater precision within a limited temperature range, typically from minus 90 degrees Celsius to plus 130 degrees Celsius. Now we are coming to the basic operation, that is the basic operation here in this case, that is delta R is equals to K into delta T, where delta R stands for change in temperature, delta T for change in resistance. So in this case, that is delta R is totally dependent on the delta T, as I have told you in the beginning only, that is when we are talking about, that is NTC and PTC, that is when there is a change in temperature, there is a change in resistance. So for this way, that is the basic operation is coming through this way only, that is delta R, that is a change in resistance, is totally dependent on the change in temperature. So what is that K? We are keeping that K as a temperature coefficient. So this is the first order temperature coefficient of resistance, where if K is positive, then the device is PTC, and if K is negative, then the device is NTC. So from this point we can say that the system is totally dependent on K. Yeah, so now here K is the hero, you can say that thing. Yeah, and the temperature coefficient of resistance T is can be measured, that is 1 by RT into dr dt. Yeah, so but we are taking that's alpha T, we are taking a temperature coefficient that's alpha T, that is 1 by RT into dr dt, where alpha T coefficient should not be confused with the alpha parameter. That's we are going to use in the next steps with the when we are going to talk about the standard equation and all those things here. So another topic I'm going to say from the basic operation, that is the as we when there is a flow in current, there is a change in temperature. So whenever there is a change in temperature, there is a change in resistance, as because delta R is directly proportional to delta T. So we can take a formula, that is I is equals to N into A into V into E, where I is the electric current which is flowing through that conductor, and N is the density of the charge carriers, and A is the cross sectional area of the material, where V is the drift velocity of the electrons and E is the charge of an electron. So now we can say that over the large changes in temperature, calibration is necessary. Totally, there should be what I can say, that if there is any change in the calibration, there may be a fault in the systems, because electronic devices use a very small amount of current, and if there is any change in a small amount of current also, the device may get affected. So there should be a good calibration is totally required. So over small changes in temperature, if the semiconductor is used, the resistance of the material is linearly proportional to the temperature. As we know that thing, that is there should be, if the semiconductor is used, whenever there is a semiconductor, the resistance of the material is linearly proportional to the temperature. So there are many different semiconductor thermistors with a range of about 0.01 Kelvin to 2000 Kelvins. As we can say, that is minus 273.14 degrees Celsius to 1700 degrees Celsius. So can you think of it, that how much they can sense? That is the standard symbol, that is the IEC standard symbol for a NTC thermistor. If we are taking, then it is minus T under the rectangle, and if we are taking the IEC standard symbol for the PTC thermistor, then it is plus T under the rectangle. So now we are going to say about the standard equation. So what is the standard equation? So in practical devices, the linear approximation model is accurate only over a limited temperature range. So complex resistance means a more complex resistance. Temperature transfer function provides a more faithful characterization of the performance, means there should be a faithful characterization, that is a performance which the system is giving, there should be a good one. So the standard equation is widely used the third order approximation, that is which we are taking, that is 1 by T is equals to A plus B into ln R plus C into ln R whole cube, where A, B, C are called the standard parameters. So now we are coming to this point, that is the parameters are specified. These parameters must be specified with the device. Yeah, these parameters should, because you will not be able to come to know that what these numbers are. So these parameters, those who are making the system, they should have mentioned these parameters on the device. So here T, that is T which we are taking, is the absolute temperature, and R is the resistance to give. So to give the resistance as a function of temperature, the cubic equation in ln R can be solved. So if we are taking ln R is equals to, as we know that the real root of which is given by, that is ln R is equals to B by 3 into C into x to the power of 1 by 3, that is x root over of cube root of x minus cube root of x. So here there are another equation, that is we are taking, that is y is equals to 1 by 2c into a minus 1 by t. So like this way we are, there are many equations, and where you can get these equations from the books also, as I'm just talking about the thermistor, what the thermistor is and how we are going to use. So I'm not going deep inside the equations, so you should, because like this way you will not be able to understand. So you're going to take a sneak peek on the all these equations from Google also, and from many sites, from many books you will get. Yeah, so now I'm going to talk about in a description man, that is I'm going to describe you that what is the NTC and PTCs do. Yeah, so now we are going to talk, that is the NTC. The NTC thermometers, that is the, in this the first point which came to our mind, what is the NTC thermometer? That is that whenever there is a resistance decrease, as direct when the whenever there is a rise in temperature, there is a decrease in resistance. So it comes in first in our mind, that is this is the function of the NTC thermometer. So what? So many NTC thermometers are made from the pressed disc, rod plate, bead or cast chip of the semiconducting materials, so such as the sintered, the metal oxides. So like this way we can say that they work because raising the temperature of the semiconductor increases the number of active charge carriers, and it promotes them in the conduction band. As we all know that there is a conduction band, there is an active band, and like this way there are many the three layers are there. So there is a conduction band, so it promotes them into the conduction band, and the more the charge carrier that are available, the more current the material can conduct. And so this way in certain materials like the ferric oxide with titanium, doping an n-type semiconductor is formed, and the charge carriers are the electrons. So now we can say that this is the system where we need doping, that is the doping of the as the semiconductor doping, an n-type semiconductor is formed. By doping we form an n-type semiconductor. So that is if we are taking the material, that is the ferric oxide, where we are doping with the titanium, that is Ti, and ferric oxide is Fe2O3, so is formed, and the charge carriers are the electrons. So in the material such as nickel oxide, if we are taking with the lithium as the doping, as a p-type semiconductor is created, where holes are the charge carrier. So these are the two types we can take, that is the p-type and the n-type, that is the nickel oxide with lithium and ferric oxide with titanium, that is for n-type, and p-type is nickel oxide with lithium. Now we can now we are going to say about PTC. What's that? PTC. So PTC is what comes first in our mind, that whenever there is a rise in temperature, there is a rise in resistance. So many PTC thermistors are made from the doped polycrystalline ceramic, that is containing the barium titanate. So what is the barium titanate? The BaTiO3, and some other components which are being mixed with it, and which have the property that their resistance rises certainly at a certain critical temperature. So barium titanate is a ferric electric, and its dielectric constant varies with temperature. So we can say that the high dielectric constant prevents the formation of potential barriers between the crystal gains and leading to a low resistance. So in this region the device have a small negative temperature coefficient. So like this way we can say that the Curie point temperature, that is the dielectric constant, drops sufficiently to allow the formation of potential barriers at the grain boundaries, and the resistance increases sharply with temperature. So at even higher temperatures the material reverts to the NTC behavior. So now we can say that the PTC are made from the doped polycrystalline ceramic, and with some other components which are contained in it. So barium titanate is a ferroelectric, and its dielectric constant varies with temperature. So that is why below the Curie point, the high dielectric constant prevents the formation of potential barriers, and that is between the crystal gains, leading to its low resistance. And so for that at even higher temperatures the material reverts to the NTC behavior. Now we can say about the PTC that another type of thermistor is the Thermistor. A thermal sensitive silicon resistor. The Thermistors employ silicon as a semiconductive component material. What? A Thermistors employ silicon as a semiconductive component material. Unlike ceramic, the PTC thermistors, the Thermistors have almost linear resistance temperature characteristic. So the Thermistors are better than the PTC, I can say that. Yeah. Now, barium dioxide thermistors can be used as a self-controlled heaters. For a given voltage, the ceramic will heat to a certain temperature, but the power used will depend on the heat loss along with the ceramic. Yeah, and now we are as I have told you already, that is the IEC standard symbol for the PTC thermistors includes the plus T under the rectangle. Now we are going to talk about the self-heating effects. Whenever, as we all know, that whenever there is a flow of current, there is some heat energy which is produced. So there should be some loss, because whenever there is a heat, there is a energy loss. Yeah. So we are going to see that what this heating effect is going to affect our device. The self-heating, it is heating on its own, it is getting heated on its own. So whenever there is a current flow through a thermistor, it generates heat, as I have told you, as we all know, which raises the temperature of the thermistor above that of its environment. And if the thermistor is being used to measure the temperature of the environment, this electrical heating may introduce a significant error, so we have to correct it. And so for that, there is an alternative method. So for example, making a sensitive airflow device employed in a cell plane, the rate of climb instrument. Yeah, let us see. The electronic variometer or a serve as a timer for a relay, as was formerly done in telephone exchanges. Yeah, so if you are taking that is the electrical power input, if you are taking to the thermistor, is just let us say that is PE is equals to IV, where I is the current and V is the voltage drop across the thermistor which is taking place. This power is converted to heat. So that power is converted to it, and this energy is transferred to the surrounding environment. If there is a thermistor which we are placing in the board, and it is getting heated, so that heat is going to be transferred to its environment. So that environment is getting the heat. Then there is a loss in energy. So that transfer is well described by the Newton's law of cooling. Now we are taking that let us tell that is PT equals to K into Tr minus T naught, where Tr is the temperature of the thermistor as a function of the resistance with R. That is, T naught is the temperature of the surroundings. So temperature T naught is getting also heated of the environment, and Tr is the temperature of the thermistor. Whenever there is a flow in current, there is a change in temperature. So where K is the dissipation constant, usually expressed in units of milliwatts per degree Celsius. What is K? K is the dissipation constant, usually expressed in units of milliwatts per degree Celsius. So at equilibrium, we can say that P is equals to PT. Whenever there is an equilibrium in the environment and in the thermistor, then we can say that P is equals to PT, that is IV is equals to K into Tr minus T naught. Yeah, the current and the voltage across the thermistor depend on the particular circuit configuration and how the circuit is made and what type of systems are used and how they are being placed. So as a simple example, if the voltage across the thermistor is held fixed, then by Ohm's law we can say that I equals to V by R. And then now it is coming, that is the equilibrium equation can be solved by the ambient temperature as a function of the measured resistance of the thermistor, that is T naught equals to Tr minus V square by Kr. These are the equations you all are going to get in the books, so you don't have to focus on the equations that I am saying. You are just going to keep in mind that T naught equals to Tr minus V square by Kr. Yeah. So as I didn't written all those things in these slides, because if I'm going to write all those things, you're going to get confused. So I'm just skipping and telling a little bit of brief on all those things. So I'm not saying all those totally. I'm not describing all those things. So now we are going to come to the applications part, where are these systems are we apply these thermistors to in our daily life. Really, first of all, the thermistor we use is in the digital thermometers, automotive that is in case of the automobiles, factories, the household appliances, many household appliances we are talking about, the circuit protection, sorry, the rechargeable batteries to measure the thermal conductivity of the electrical materials, many useful in many basic electronic circuits, temperature compensation used in the Wheatstone bridge, and many uses are there of these thermistors. Really, these are the things we should at first get some idea before we are going to get in the main and the depth of the instrumentation engineering. So these are the points we should keep in our mind, that the where the thermistors are being used. So if you guys like the video, please subscribe, share it, and press the like button, and please click on the bell button, because you should get the notification whenever I'm going to upload a video, because each and every video is going to say you something, each and every give you some idea that what an instrumentation engineering and what they are using in our daily lives, and why should we use and all those things. So really, thank you to all of you. Thanks a lot.